Hi, everyone. Thank you for tuning in today. I'm Carrie Ann Raicato, Director of the Office of Climate Change Technology and Research at Connecticut DEEP. Welcome to the Exploring Climate Change Solutions webinar series. The series is brought to you by the Governor's Council on Climate Change. On April 22nd, 2015, Governor Malloy issued an executive order creating the Governor's Council on Climate Change, also known as the GC3. The Council is charged with examining the efficacy of existing policies and regulations designed to reduce greenhouse gas emissions and to identify new strategies to meet the state's greenhouse gas emission reduction targets. The Council is composed of 15 members from state agencies, quasi-state agencies, businesses, and nonprofits. To learn more about the GC3, please go to www.ct.gov/deep/GC3. The webinar series explores innovative and successful climate change solutions in Connecticut and the nation. The series provides firsthand accounts of high-profile municipal climate programs, climate initiatives in the corporate world, new greenhouse gas reporting frameworks, statewide sustainability programs, low-carbon fuel initiative, and other programs and projects that help reduce greenhouse gas emissions and improve climate resilience. Today, we're excited to have Joe Swift from Eversource as our guest speaker. Joe will explain the basics of renewable thermal technologies, review viable applications for homes and businesses in the state, and identify current financing and incentives that enable further adoption of these technologies in Connecticut. Joe's presentation will be about 40 minutes long, and then we'll open it up for questions from the audience. If you have questions, please submit your question in the question box, and we'll read it aloud for Joe to respond to at the end of the presentation. And before we get started, for those of you listening via your computer speakers, if you're experiencing poor sound quality, I do encourage you to call in using a landline or a cell phone. So with that, Joe, thank you again for your willingness to present today, and I'm going to go ahead and turn it over to you to go ahead and get started.
Excellent. Thank you very much, Carrie. My name is Joe Swift, and I work at Eversource in the Energy Efficiency Department. I'm the Operations Supervisor for Planning, Evaluation, and Regulatory work, and I want to thank you, Carrie, for providing me the opportunity to present today. I'm also here with Sabrish Menon. He's a co-op student that works in our department from Northeastern University, so if there's any difficult questions at the end, I'm going to turn them over to Sabrish. So, the overall topic is renewable thermal technologies, a big part of which are heat pumps. Included in renewable thermal technologies are solar thermal, biomass, and biodiesel. The presentation, for the most part, is going to just focus on heat pumps, and specifically, hopefully, I designed this presentation so there'll be a little bit of something for everybody. Some of the presentation is very basic, explaining just high level what a heat pump does, but then we're going to kind of dive into some, operating costs and emissions factors for different types of heat pump technologies and some different design considerations to consider when you're making the choice about what type of HVAC system or what type of technology you can install in your house. What this presentation hopefully will not do is provide specific answers to everybody, because as we run through this, hopefully the key takeaway will be that there's a lot of factors and a lot of complexities involved when deciding upon any type of HVAC system or technology that can be used in a home and business. So I'm going to try to hopefully point those out and show examples of where heat pumps may work or where they don't work, and what are some of the benefits and what are some of the potential disadvantages, and leave it to you to kind of hopefully just get the basic understanding of some of the different characteristics of different types of technologies in heat pumps. Well, moving on. Usually when I do this presentation live, I'll ask the audience if anybody has a heat pump in their house. And, if there's 50 people sitting in front of me, maybe 1 or 2 people will raise their hand. And then the next question that I'll throw out to the audience is, well, nobody here has a refrigerator. Is that what you're telling me? And then all of a sudden people kind of get this puzzled look on their face, and more hands start to go up. And the reality is heat pumps really operate exactly like a refrigerator. The technology is fundamentally no different than that used in a refrigerator. Essentially what refrigerators do is they remove heat or thermal energy from the inside of the refrigerator, and through a refrigeration process, they dissipate that heat to the coils on the backside of the refrigerator. You know, and really, fundamentally, that's exactly what heat pumps do. They're able to move heat from low temperature to high temperature through a refrigeration process. And we'll get into some of the more specifics here when we get into the presentation. Now, I wouldn't necessarily call it a disadvantage, but one characteristic of heat pumps that you should be mindful of is that their heating capacity and efficiency is generally lower with lower source temperatures. And what I mean by that is if you have a heat pump operating on a cold winter day, it's not going to have the same capacity or the same efficiency that it would have on a milder day like today, as an example. Likewise, when they reverse themselves and provide cooling, they're going to be most efficient and provide the most capacity on a 75 or 80 degree day. When it's 90 or 95 degrees, their capacity is going to be a little bit lower and their efficiency is going to be a little bit lower. And I think we know that intuitively from the cooling side, but it also applies to the heating side as well. And as we move through this presentation, you're going to see examples of how this works and what are some of the design challenges, and ultimately what are the effects of having a heat pump technology where the capacity and the efficiency varies versus a traditional fossil fuel type of system where the efficiency and the capacity remains pretty much constant, relative to the outdoor temperature. First type of heat pump we're going to talk about is the ground source heat pump, also known as a geothermal heat pump. I personally prefer the term ground source heat pump. People think of geothermal and they start to think of these hot springs and things of that nature. And the geothermal heat pumps aren't really tied to hot springs. They're really just tied to the earth. And the earth, once you get below the frost line, is typically around 50 degrees Fahrenheit in this climate. They have a higher efficiency than air source heat pumps because it could be 10 below zero outside, but once you get 6 or 7 or 8 feet down below the surface of the earth, the temperature is going to be, again, relatively stable and around 50 degrees. So they're able to provide fairly efficient heat, or very efficient heat, even on a cold day because they're tied to the earth. Likewise, in the summer, it could be 95 degrees out, but they're taking the heat from the inside of your house and dissipating it into the ground. How they do that is through a series of pipes that are basically either buried in the ground or drilled horizontally into the ground. So, with the geothermal system, you're going to have some type of piping network that's going to basically couple the heat pump to the ground. Most often in Connecticut, these are vertical boreholes that are drilled, and there'll be a polyethylene, which is essentially a hard plastic pipe that's inserted into the borehole. Less common applications are what you see on the bottom right, which is a trench that is dug, and in this case it was essentially a slinky type of pipe configuration that's buried into the ground. These pipes carry water. There is a propylene glycol antifreeze solution that's added into the pipes just to prevent them from freezing. And I know folks here, they hear the word antifreeze and they tend to panic. But essentially, the propylene glycol is a food-grade antifreeze, and you can find it all over the shelves of your supermarket, and even in places like Dunkin' Donuts. It's flavored iced teas, certain types of ice cream, frosting, cake mixes, salad dressings, and my favorite, even Fireball cinnamon whiskey contains some level of propylene glycol. So I think it appears to be a fairly safe type of antifreeze choice for use in ground source heat pumps. Ground source heat pumps are the most efficient type of heat pump, but they're also the most expensive type of heat pump, mainly because of the ground coupling that takes place. The size of either the boreholes or the trenches varies with the load on the home, which typically is tied to the size of the home. So, for a typical residential system, you might be paying on the order of $30,000 to $40,000, or sometimes higher if it's a larger house, sometimes less if it's a smaller, more efficient house. There is, however, a 30% tax credit that is available to help reduce the cost of installing a ground source heat pump. And here's another good example. If you're confused about ground source heat pumps, just take a look at this picture right here, and I'm going to argue that this essentially is a reconfigured open loop ground source heat pump. If you're from New Jersey or Boston or Wisconsin, you'd probably call this a bubbler. Around here we call it a water fountain, but it really is, if you think about it, an example of a ground source heat pump, and I'm going to explain why. Because if you look at how this water fountain works, warm water, and when I say warm, it may not be warm, it may be, let's just say 60 degrees, is going to enter from the ground or the water main. It's going to go into the device, and heat is essentially going to be removed from that water to make the water cold. So you have warm water coming in, heat is removed from the water is now cold, which is going to, obviously, you know, the cold water is going to come out of the top of the water fountain. That heat has to go somewhere. So you're going to have, on a water fountain, cold air coming into the water fountain. It's going to absorb the heat, and it's going to exit the water fountain as warmer water. It's simply just, you know, trading energy or trading BTUs. So, you know, theoretically, you could take a whole bunch of these and install them in your home or business and just let them run, and you could provide a heating source. Probably wouldn't be very efficient. It would be a huge waste of water, but theoretically, this would work, and it's working because essentially it's a modified type of ground source heat pump. I hope everybody likes that slide. Sabrice helped me put that together. So.
Very clever.
Thank you. A more common type of air source heat pump is, or a more common type of heat pump is an air source heat pump. And again, the same technology, but unlike a ground source heat pump, they're not coupled to the ground. They're essentially using the heat that's in the outside air and extracting energy from that outside air and compressing that and using that to heat your home or office. Likewise, in the summer, they'll reverse themselves, and they can remove heat from the inside of the building and dissipate that to the outside. So the, you know, heat pumps are reversible. They provide heating and cooling. And again, unlike a ground source heat pump, they're using the outdoor air as the heat sink and the heat source. Typically, you know, the heat pumps that we see are generally ducted heat pumps, or traditionally have been ducted heat pumps. In recent years, we're starting to see a much higher penetration of ductless heat pumps, and we'll talk about those a little bit later. But basically, the bottom two right pictures show a ductless heat pump, and again, they're not as efficient as ground source heat pumps. And the reason, again, is that the heating performance drops as the outdoor air temperature drops, and likewise, the cooling performance, meaning the capacity and the efficiency, drops as the outdoor temperature rises. Now, most of you have probably heard about some of these newer generation heat pumps and newer generation ductless heat pumps. They are greatly improved compared to heat pump technology 10 or 15 years ago, and they can provide value in cold climates, but they're still not 100% perfect. You know, when you get to temperatures below, you know, 10 or 15 degrees or 5 degrees, typically, in most cases, there are exceptions, but in most cases around 10 or 15 degrees is the critical point where the heat pump may not quite be able to keep up with the load, and you're going to have some type of backup system to provide the difference. I mentioned new generation cold climate heat pumps, and here's a chart from a leading manufacturer of ductless heat pumps. And essentially, the blue line that you see on the bottom right is the heating capacity of, I'll just call it an older generation type of heat pump. And you can see at around 14-degree outdoor temperature, the heat pump can only provide about 60% of its rated capacity. Typically, older generation heat pumps, oftentimes you wouldn't even think about using them if it was below 20 degrees. You would resort to some type of backup electric resistance or some other type of backup system. Again, you can see the sharp decline as you go from a 50-degree outdoor temperature to a looks like about a 14-degree outdoor temperature on the x-axis. Some of the newer generation heat pumps will still provide a very high amount of heating capacity at temperatures, as low as 13 below zero. And you see two different models plotted on this chart, and both of those models at 13 degrees below zero still can provide about 80% of their nominal rated heating capacity. That's great news. I think that's phenomenal news, and it's really helped ductless heat pumps, I think, become a more viable option in Connecticut. However, we're finding that, when the temperatures do get below zero or get close to zero, customers still need to either, put on a sweater or use some type of backup system. This is probably the most complicated slide that I have in the whole presentation, so it's going to take me a few minutes to go through this. But essentially what I tried to do is I plotted several different things on this graph, and I'm going to start with the blue line at the bottom right. Essentially, this is a hypothetical home. It's not a real home. I made these up, but it's typical of what you might see if you were to kind of dive into the design of a heat pump on a typical residential home. And you'll notice that around 45 degrees, which is the x-axis, if you follow that across to the y-axis, that represents the heating load. So at around 50 degrees or maybe a little over 50 degrees, you really don't need any heat, even though you probably want the temperature inside your home to be 64, 66 degrees. Typically, if it's 52 or 55 degrees outside, you're going to have enough internal gains and solar gains, so your heating system won't have to run. Now, if you kind of keep following that blue line all the way up, as it gets colder, you'll notice that the heating load that your house needs starts to increase, all the way to the point where we're at 10 below zero, and this house might need 35,000 BTUs of heat to be able to satisfy the thermostat. That's the first line. If we look at a typical ductless heat pump, ductless heat pumps have the ability just to basically match the load. So, at temperatures, is the temperature, if you start at 45 degrees, the ductless heat pump's going to be fine. As you move up the scale, ductless heat pump still could potentially, is still going to be able to serve the load, and somewhere, and this number varies, but let's just say somewhere around 10 degrees, now the ductless heat pump isn't going to be able to maintain or satisfy the thermostat in the home. And we saw it on the previous slide how, they work good, they work much better than previous generation heat pumps, but their performance is still going to start to decline a little bit as the temperature gets close to zero or below zero. And basically what you see, this little triangle here, is the gap that's left between the heating load on the house and what the heat pump is able to provide. And, when you look at this graph, the first thing that probably might jump out in your mind is that, wow, that's a pretty big triangle. Don't I want my, should I make my heat pump bigger in order to satisfy that load? Because that looks like a fairly big chunk when I'm comparing it, at least to the the size of the triangle relative to the rest of the graph. And my answer is maybe. And the reason I'm saying maybe is because if you look at typical weather in Connecticut, 0 degrees, 5 below, we may only have about, a handful of hours each year where the temperature is 0 or below 0. So if you do the math, and if you do the math on this, if you look at a typical weather year in Connecticut, you're going to find that that triangle really only represents about 2% of your overall heating capacity, because you're looking at the temperature difference, but you're also looking at the number of hours. In other words, most of your winter takes place out here. You have cold temperatures, but you don't really have that many hours with cold temperatures. So, when you're designing a heat pump, this is one of the challenges you face. It's like, what do you want to do with this little triangle? Do I want to eliminate this little triangle? And you certainly can, but it means either putting in a larger heat pump or maybe adding some insulation or doing something to eliminate that triangle. In other words, it's going to cost more. It's going to cost more to eliminate that triangle, and is it really worth the time and effort and the cost to eliminate that triangle just to avoid 2% or 3% of the overall heating consumption. And last but not least, this green line just represents the COP of the heat pump, and we talked about how the performance will be higher, or the efficiency will be higher at higher temperatures, and the efficiency will drop down much lower at low temperatures. So it's a busy graph, but I think it was a very, very important graph to kind of conceptually present how a heat pump works and how it interacts with the load on the house and so on. Here's another graph that we put together, and this graph represents source energy. So I want to be very clear, this graph doesn't represent customer cost. It's just essentially looking at how much total energy do each of these technologies require to deliver one source of energy back to the end user. So if you look at electric resistance, the number that we're coming up with is about a 0.33. And you say to yourself, well, why is that at 0.33? And the reason is because power plants have to use energy to generate electricity. They're certainly not 100% efficient. Now, granted, some of our generation is renewable sources, but a lot of it isn't. So this is kind of like a weighted average of our generation fleet in New England. And then in addition to that, there's line losses. So when you're all said and done, it takes about one unit of energy at the power plant to generate about 1/3 of a unit of energy to the end-use consumer. As we move across, you look at the oil, and we plotted these using just kind of a higher and lower efficiency, because oil furnaces might range in efficiency from 70-something to like high 80s. So, we tried to account for the range of different oil efficiencies on this graph. So, two things are happening. Number one, the oil boiler or furnace, whatever device you're using, isn't going to be 100% efficient. But we're also taking into account that for each gallon of oil, there's about another 15% or so adder that you have to include that takes into account the energy that it took to extract that oil from the ground and deliver it to your home. So from a source BTU basis, oil is much better than electric resistance, but it's still not even at close to 100%. Likewise with gas, we're coming in at around 82%, depending on, or up to 82%, depending on the the type of, or the efficiency of the gas furnace. Likewise, we've added in the cost of energy to bring gas to your home, which it was lower than the oil. I don't remember the actual number, but I think it was on the order of less than 10%. Last but not least, now we get into the heat pump scenario, and again, depending on the heat pump and the efficiency, you'll see that the source BTUs can either be below 1, if it's a 1.5 COP heat pump. As you move up the scale to a 2.7, which might be an efficient air source heat pump, we're kind of almost at the break-even point of getting more than one unit of energy, more than 1 unit of source energy out compared to 1 unit of energy put in. And as you move to the top, you'll see up here a COP of 4, which represents an efficient ground source heat pump. And you can see from a source energy basis, it's probably it's the best technology that we have out there. And again, this is not a cost representative; it's just looking at source energy. Now we'll jump into the costs and take these costs for what they're worth. We put the assumptions down in the table below. For example, we assumed oil cost $2.42, which was one of the latest numbers we could find, and we assumed an efficiency of 85%. And likewise with the other technologies. And if you look at from a cost per MMBTU or a million BTU basis, we're looking at natural gas being a little bit below $20, a ground source heat pump $17 or $18, oil around $20, an efficient air source heat pump being a little over $20, and moving on to propane, and electric resistance is around $55 per MMBTU. So these costs really represent costs that a consumer would pay for the energy that they would get out of these units. Moving over on the right axis, we see emissions. And again, these emissions are a little bit complicated because, you know, when you're burning oil, we can apply emissions factors to the oil, and we can come up with how many pounds of carbon are emitted per MMBTU. When we look at likewise with the gas and propane, when we're looking at electric resistance, we're taking into account, you know, the makeup of the generation that supplies Connecticut. And you'll notice that, you know, even though natural gas and the geothermal heat pump are fairly comparable in costs, the ground source heat pump has the lowest emissions, and again, that has to do with a combination of, you know, the heat pump being very efficient, so it's able to offset the fact that the generation fleet is not 100% efficient. In fact, it's more than able to offset that difference. And as we went through this, we started to realize that the world is changing. You know, back in around the year 2000, when I first came into the company, I remember paying less than $1 per gallon for oil. And at that same time, natural gas was about roughly, let's just say, $1 per CCF. So back in the year 2000, if I wanted to make a decision in terms of which fuel I wanted to install in a home based on purely economic reasons, it looks like oil would have been the winner. Moving on, we all know what happened to oil 4 or 5 years ago. It started to skyrocket, and people were paying $4 or more for oil, which made it a less attractive fuel in terms of cost effectiveness or you know, low utility bills, if you will. Likewise, at the same time, gas went up, but we certainly didn't see the sharp decrease in gas prices that we saw with oil. So back maybe 2 years ago, it was almost like a no-brainer that if you had a choice between oil and gas, all things being equal, you would probably want to install gas in your home, because on a cost per BTU basis, it made a lot more sense. But then kind of, you know, the world kind of turned upside down yet again, and late in 2015 and going into 2016, we've seen oil prices drop. So I guess the short answer is I don't know. If I knew it was going to happen, I don't think I'd be working here. So what we tried to do is we tried to put a forecast together, and this is very unscientific, but I think it's probably as good as any forecast, because forecasts by nature seem to always be wrong. And we plotted, you know, the green line is the cost per MMBTU for electric resistance, and I think it's fairly safe to say that that appears to be the most expensive technology, both in the past and going forward. We also plotted electric heat, essentially a ground source heat pump, an electric heat pump, or an air source heat pump with a COP of 2.5, and looked at oil and natural gas prices. And kind of what you see here is a big mess. It's kind of like a tight horse race at this point. And depending on where we go in the future, you know, we may ground source heat pumps appear to be leading the charge, but between conventional heat pumps and oil and natural gas, it's too hard to predict. You know, if you could predict this, you probably won the NCAA office pool, but I don't know. The future is uncertain. One thing to consider, though, even though I just showed on that last slide that heat pumps and oil were about comparable, one interesting observation about heat pumps is that depending on the temperature, you may want to opt to use a heat pump, and then when it gets cold out, resort to a different type of fuel. Now, I've got a heat pump. I've got a ductless heat pump in my house, and based on my own experience, last year I used the heat pump probably about 95% of the time and burned very little oil. This year I used the heat pump in, you know, December and January. It wasn't too cold. In February we started to get some cold weather, and I started to use my oil system more. And this graph, this is hot off the press. This came out of a study that came across my desk just about a week ago, but this does a great job of illustrating that, you know, when it's cold outside, heat pumps are a more expensive technology, but depending on the efficiency of the heat pump, if its temperatures are above 30 degrees, maybe it makes sense to use a heat pump. So, and we know from experience that a lot of customers have installed ductless heat pumps, especially in homes, and left their oil system in. So even though, on an average basis, it appears to be a dead heat, there still is an opportunity for customers like myself to use the heat pump in warmer weather, and when it gets very cold, put on, resort back to my oil system. So, to sum it up, or start to sum it up, if we look at heat pumps and some typical examples of where they may be used or may not be used, in general, and these are generalities, if you have natural gas, I would probably say that in most cases a heat pump may not make sense. You can go back to this graph and say, well, it might make sense under warmer temperatures and don't use it under colder temperatures, but in general, I would say, natural gas compared to a heat pump probably isn't going to make sense. We see some customers do it. I personally, I don't think I would, but obviously, as I mentioned earlier, we don't know what's going to happen in the future. If you have oil or propane, maybe a heat pump makes sense, and we'll talk about some of the different applications and how they work in a few slides. And as we saw in a couple of those slides, electric resistance is by far and away the most expensive type of heat we can have. So I would say in general, electric resistance homes are a good candidate for some type of heat pump technology. And last but not least, we're starting to see some very low load homes being built. And low load, typically, I would say maybe 10 years ago, we didn't see too many air source heat pumps being installed in homes. We're starting to see very, very efficient homes being built, and oftentimes those homes either rely upon a very small ground source heat pump or a ductless heat pump system. And the photo you see at the bottom is actually a builder out of Massachusetts. So it's colder up there. He's up towards the Berkshires, so it's a colder climate than what we have here in Connecticut. And his typical home has a two-zone ductless heat pump, one zone for upstairs, one zone for downstairs. And I forgot the cost of these systems, but I think the cost of his total heating and cooling system is only about $8,000 or $9,000 installed, and it provides 100% of his heating and cooling in the home. What he does how he achieves that, however, is he takes that savings that he gets from the heating system and he invests it in the shell of the home. So this home looks like a typical home from the outside, but upon closer examination, you'll find that the walls are, 16 to 20 inches thick and filled with insulation, and the ceiling has probably an R50 and an R60, so it's an extremely well-insulated, tight home, and as a result, he can get away with a very low-cost, small type of heating system. So again, just some of the different options. The house on the left it's not my house, but it looks kind of like my house. I picked this photo because it's a little better looking than my house, but some of the different options that I had available to me is I could take a single zone ductless heat pump in and put it in and offset some of my oil, and ultimately that's what I chose to do. It was a relatively inexpensive upgrade. You can shop around and put a single zone ductless heat pump in for probably less than $4,000 if you do your homework and do some shopping. A different option would be to install a 2- or 3-zone system. Provides a little more savings, a little more comfort, but it comes at a higher cost. I could have also decided to install a ducted heat pump. Again, now we're talking ductwork, so an added cost, but again, it would provide heat throughout all the different rooms of the house via the duct system. And last but not least, I could have installed a ground source heat pump. Very efficient, would have provided the most efficient heating and cooling for my home, but again, the price tag would probably be on the order of 10 times as high as the lowest cost option, which was the single zone heat pump. And when we look at ductless heat pumps in particular, I talked about how in my home I put in just a single zone ductless heat pump, and typically if we look at HVAC systems or if we look at a typical house, you're going to have either baseboard or duct supply registers throughout the house providing heating and cooling to every single room, and that's kind of what's modeled here. These little black things represent either baseboard or ducts that are providing heat to the home. One of the strategies that we see used with ductless heat pumps is, rather than try to replace your total heating system, is you simply install a ductless heat pump in the main living space of the home. Now, the benefit of this is that it's certainly it's kind of like putting in a pellet stove. You just put one unit in and you're done. It's a less expensive option, and you're going to generally get a bigger buck for your savings, because you're heating the primary living space on your home. The disadvantage of this type of system is that you're going to have a cold, generally you're going to have a cold bedrooms or cold bathrooms, and in my house I don't mind. I put on a sweater or I turn on my oil system, but so it's a trade-off. It's really a comfort versus a dollar trade-off when it comes to going this option or going the single zone option that we see with ductless heat pumps. This is actually a different house that I owned, and I plotted some points. I'm going to kind of rush through these so we have time for questions. But essentially, what I did is I had electric resistance in this house, and I also put in a ductless heat pump, and I alternated weeks between the ductless heat pump and the electric resistance, and I plotted the lines, and you basically see the ratio of these lines essentially gives me the COP of the estimated COP of the ductless heat pump, and it came in around a 2.9, which was very good. I was pleased with this. But at the same time, it's no guarantee that all ductless heat pumps are going to operate at a 2.9, because there have been other studies out that have shown that the COPs vary between 1.5 and 3, depending on the design of the system, the location of the outdoor unit, the temperature of the return air, and so on and so forth. So they're somewhat difficult to. Their actual performance is a little challenging to try to predict. And here's another screenshot of a test that was done on a ground source heat pump home in Connecticut, and you'll see the COPs that range in the 3 to 4 range. So again, a very, very efficient system, again, because it's using the ground as the heat source versus the outside air as a heat source. And unlike my ductless heat pump in my home, this system is able to provide even heat and even cooling throughout the home versus being able to provide it just to one zone. And I'd be remiss if I didn't talk about the rest of the house. And I think it's important when you make any type of upgrades to heating systems, you have to also consider the shell of the house and making sure that you've taken care of the higher priority items first, and you've looked at the insulation, and you've tightened up your home, and you've looked at your ducts and everything else. And one advantage of ductless heat pumps is you don't have to worry about the ducts because they don't have ducts. But if you do have ducts in your house and you're replacing your heating system, you should consider insulating or sealing or even replacing your ducts before you even make that investment in the heating system. And we're moving on towards the end. I want to talk a little bit about heat pump water heaters, which are essentially an air source heat pump. The technology's been around since, I don't know, probably 20 years. We're starting to see a higher penetration of heat pump water heaters. They're generally 2 to 3 times more efficient than electric resistance water heaters. And so if you have an electric resistance water heater, this might be a cost-effective technology. Likewise, with ductless heat pumps, we were starting to see a lot of these systems replacing oil hot water heaters, and one benefit that we get out of heat pump water heaters, and when we talk to customers, is that they also dehumidify. Oftentimes, customers will say, "Geez, I know I'm saving energy because my utility bills have gone down, but now I don't even need the dehumidifier in my basement because it actually dehumidifies through the heat pump process." And finally, I'm not going to read all of these, but there are a lot of information on the website about different energy efficiency incentives that are available through the utilities, as well as a number of different financing options that are available as well. So just to summarize, and heat pump technology is kind of cool. It's interesting. It's improving. It offers a lot of different solutions to many different customers and their situations. However, as I mentioned, current fuel prices, I wish we could predict them. It would make my life a lot easier. We had a department meeting yesterday, and we were kind of talking about, when we go home at night, we're glad oil prices are low. When we come to work, we kind of wish in some ways that oil prices were higher, because it would make some of these choices that our customers face a little more, at least it would make the choice in terms of what to do a little bit easier. And when you look at replacement options, it's not always a replacement option. Sometimes it can be a displacement option, and once again, it's not as easy as it's not a plug and play type of decision. You have to consider, what type of technology do I want to use? What comfort, what are the comfort ramifications of one technology versus the other? What are the cost ramifications? What are the environmental ramifications? We saw the different emission slides. And then you also have to consider, geez, should I be upgrading my shell? And I don't want to forget about my hot water. So there's a lot of different convoluting factors that get kind of thrown into the mix here. And it seems like every situation is a little bit different. So hopefully this presentation gave you, food for thought in terms of some of the different things that you should think about if you're thinking about any type of HVAC or technology upgrade in your home. And that's all I have.
Great, thank you, Joe. That was really a great presentation, and we were having trouble here thinking of questions to ask because you covered everything. But we came up with some, and others who are on the webinar, please go ahead and send yours in, and we'll read those out loud. So to start with, just some basic questions around, are we seeing a greater adoption of air source heat pumps in Connecticut and New England? Is this technology becoming, more well adopted?
That's a great question, and I don't have any numbers from 2016, but anecdotally, I know participation has slowed down a little bit. The high oil prices definitely drove a lot of customers towards heat pump technologies, all types of heat pump technologies for that matter. Geothermal, conventional heat pumps, and ductless heat pumps. So we're seeing activity slow down, and one interesting thing that we're seeing too is that customers like myself that have heat pumps installed in their oil homes are using them exactly like I'm using them, meaning that they'll still use the heat pump, and they'll use it when the temperatures are above 30 degrees, and when the temperature drops below 30 degrees, they're relying more upon their oil. And again, that's just based on the economics today, and we don't know what's going to happen next year with oil prices. So, but yes, we have seen in recent years a much higher proliferation of heat pumps, especially the ductless technology.
Okay, and the ground source heat pump, is that more common for residential or more common for larger facilities?
Probably more common for residential. We see some installations going into schools and some larger types of commercial buildings, but generally, at least the ones that come through our programs are generally more residential. A lot of those are new construction, and again, the advantage of going with new construction is that you can take care of the insulation and the shell and the efficiency of the home first, and then you can put in the ground source heat pump. But again, 4 or 5 years ago, there were some era dollars available, and oil prices were still high, so we were seeing a lot of retrofit geothermal installations take place during that time frame. And when I say a lot, it's not thousands; it's on the order of maybe several hundred per year, but it's still. So it's not I wouldn't call it a mainstream technology, but I wouldn't call it really an emerging technology. It's been around for years, and we've seen many successful applications.
And if someone is interested in looking at this for their home, how do you find installers in Connecticut? Are these technologies something they're familiar with? And is there any tips or questions a customer should ask when interacting with the installer to learn about these technologies? My
primary recommendation is to find an installer that is comfortable with the technology, because my experience is there are HVAC contractors. I think all HVAC contractors, know what a geothermal system is. That's not the issue, but I think it's engineering the systems takes a little bit of a sharper pencil compared to just putting in, like, an oil boiler as an example. So my recommendation would be to find an installer that does these systems or installs these systems as a primary part of their core business. And there are a number of installers out there that number of great installers in Connecticut that do install ground source heat pumps.
Great. And then you had the picture of the house in Massachusetts that had, significant insulation and I think you said R60 walls. Is there incentives for like a bundled approach to installing these air source heat pumps, in that you do insulation at the same time as you put in air source heat pump?
Yes. Well, through our new construction program, and again, I want to caveat that R60. I'm not sure if it was R60, but it was a high number. But if you participate in our residential new construction program, there are bundled incentives that take into account, the total efficiency of the home based on the HERS rating. So, a home like that, would qualify, based on the HERS rating of the home for a significant incentive, based on, again, a combination of the efficiency of the home as well as the efficiency of the heating system. And I want to throw in one other anecdotal point, about homes like that. In Connecticut, we have the Zero Energy Homes Challenge, where we recognize builders that have built some of the most efficient homes in the state. And when you talk to these customers, it's amazing. You would think they would talk about the energy savings, but the first thing that comes out of their mouth is how comfortable these homes are, and how healthy the homes feel, and how quiet the homes feel. So I think that's, you can't lose sight of the non-energy benefits of energy efficiency when you're making these types of decisions.
That's a great point. A few more questions. Can you go back to the slide that shows the graph on measured versus predicted efficiency, and spend a little bit more time, I guess, explaining that?
Was it the geothermal slide?
Measured versus predicted efficiency. I'm not sure. If the person who wrote that question can clarify a little bit more. And while we're waiting for that, what do you think that the COP will get to in the next few years?
I don't know. I mean, we're starting to see air source heat pumps which have, HSPFs, which is not quite the COP, but it's a similar measure of, 13 or 14. So, likewise with ground source heat pumps, we're seeing, COPs, approaching 5 or maybe even 6 at this point. I haven't looked at some of the literature lately, so it's, they're getting up there. I want to caveat that though, and the rated COP isn't always necessarily what you're going to get out of the unit too. There's a lot of design factors to consider, in terms of making sure that your ductwork is designed properly, that if you're installing a ground source heat pump, that your ground loop is installed and sized properly, and if you have a ductless heat pump, you don't want to leave it outside on the ground where it might get buried with snow, otherwise it's really not going to perform at all. So there's a lot of different parameters that have to be considered when you're comparing rated efficiency versus, the actual efficiency.
Great. So yeah, I just got a note saying the slide that you're on, yes, if you could talk through that a little bit more.
All right. Yeah, I apologize. I kind of rushed through the slide because I wanted to make sure we had time for questions, but I'll be happy to answer that. So essentially, this is a two-stage ground source heat pump, meaning it can, it can either operate like at maximum speed or maximum output, or it has the ability to throttle down and operate at, I'll just, at 3/4 speed to be more efficient. So the green line that you see is the predicted operation of the ground source heat pump at part load conditions. And along the horizontal axis, we see, the ground loop temperature. And the red line or the maroon line is basically the predicted performance of the ground source heat pump when it's at maximum output. In other words, when it kicks into high gear and the thermostat is calling for more heat, it'll essentially ramp up to the red line and then produce maximum performance. On the horizontal axis, again, we see ground temperatures. Now, I mentioned how in Connecticut the ground temperature is around 50 degrees year-round, which is true, but when you operate a ground source heat pump throughout the whole heating season, the earth around the ground loop will start to become a little bit cooler because you're extracting heat. So the water that's coming in from your loop may vary from 55 degrees maybe in November, and probably out here where the temperature was around 35 degrees, we saw this probably took place in late winter when the ground loop probably cooled off a little bit. But the scatter lines here were actually the measured COPs that this unit saw. In other words, an engineer went out there and was taking measurements of water flow and water temperature and power use, and was able to calculate what the actual COPs were compared to the rated. And they're lower, and they're not alarmingly lower. In fact, they're expected to be lower because these rated COPs don't fully account for some of the pumping and fan costs of the geothermal unit, whereas these measurements did fully account for the total consumption of the unit. So it's I would characterize this as a good performing ground source heat pump. It looks like it's got a COP of a measured COP approaching 4. And back to your earlier questions, if we looked at some of the newer ground source heat pumps that are out there, these rated lines would shift up probably to the 4.5, 5, and maybe even 6 COP range, and hopefully we'd expect the actual performance to also shift up and follow suit and shift up as well. So I'm sure there's probably actual COPs out there that are in the 4 to 4.5 range for ground source heat pumps.
Great, thank you. So that's all the questions that I have for you today. We really appreciate you, putting together the slides and talking us through them. I think this is really informative and will be a great asset to us as we, look to GHG mitigation and what needs to happen in the building sector. If those of you on the line have further questions, Joe's kindly put up his contact information. We will post the slides and the recording on our website. Thanks, everyone. Have a great day.
Thank you, everybody. Good job, both of you.